Dear friends, this is the lecture number 3 of magnetism and matter. In the previous lecture, we discussed about geomagnetism, how Earth behaves like a huge magnet and its parameters, declination, inclination and horizontal components. But in this lecture, we'll discuss about neutral point. Then we'll discuss how current carrying solenoid behaves like a huge magnet. Then we'll discuss about Gauss law in magnetism. So let's first start from neutral points. What do you mean by neutral points? I have told you in the previous lectures that Earth behaves like a huge magnet. So everywhere magnetic field of Earth present, everywhere. It may be inside a closed room or it may be anywhere. Magnetic field of Earth is present. So at any place you will keep a magnetic needle that must remain in north-south direction. At any place you keep, any place on the surface of Earth you keep one magnetic needle that must deflect, pointing north-south direction. But there again some places we will find. Again some place we will find where the magnetic needle will not deflect. Is it possible? Is it possible some place we will find where magnetic needle is not deflected? Magnetic needle not deflect means there is no magnetic field. Magnetic field not deflect means there is no magnetic field. Is it possible? Yes. But that we can make it. We can make it. How? We will keep our magnet, our bar magnet or any magnet we will keep. So what will happen? At that point, suppose I will tell you this point. At this point, Earth has its magnetic field. And our bar magnet which one we will keep? It also provides its magnetic field. Our bar magnet will provide the magnetic field here. Earth has also its magnetic field. When magnetic field of Earth, basically horizontal component of magnetic field of Earth will be equal and opposite, equal in magnitude and opposite in direction to the magnetic field of our bar magnet. Then at that point magnetic field, net magnetic field will be 0. But initially it was not 0. Initially at this place magnetic needle deflect. But if we keep a bar magnet, then Earth magnetic field and the magnetic field due to our bar magnet cancel each other. And at this point, now if you will keep a magnetic needle, that needle will not deflect because there is no magnetic field. That needle will not point in north-south direction. That needle can remain in any orientation. It will not suffer SSM, it will not point the direction north-south. So that point is called neutral point. So neutral point is a point where horizontal component of a magnetic field of Earth is equal in magnitude and opposite in direction to the magnetic field of a bar magnet. So where actually these points are present? If I will keep a bar magnet, we can have the neutral point. If I will keep a bar magnet, we will draw the lines of forces around the bar magnet. Suppose here I will keep a bar magnet. Around this bar magnet, everywhere the magnetic needle will deflect, but some places only you will find 2 points where the magnetic needle will not deflect around it. You can check keeping that magnetic needle at different places where the needle is not deflecting. That point is called neutral point. But exactly where is the position of that neutral point? Now let's see. To know that, suppose This is the geographic north. This side is geographic north and this side is geographic south. If this is geographic north, so here is the magnetic south and here is the magnetic north. Magnetic north. So how the lines of forces of earth move? Earth lines of forces move from north to south. Means in this direction earth lines of forces move. I am just showing like this. In this direction earth lines of forces moves. Okay, from north to south they will go. Lines of forces will move from magnetic north to magnetic south in this direction. From north to south. So if I will keep a bar magnet, I will keep a bar magnet like this, you see. Bar magnet I will keep. What will happen here? Lines of forces are going from north to south direction in this way, because everything happens in magnetic meridian. Everything happens, otherwise I will showing you like this. North to south the lines of forces are going. Here north to south lines of forces are going. So if we will keep a bar magnet here, but how we place the bar magnet? Two cases comes here. First case, north facing north. North facing north means north pole of the bar magnet is facing to the geographic north. North facing north means this north is geographic. Always remember, this is geographic north. So north pole is facing to north pole. So what happens in this case? Now let's draw the magnetic lines of force due to this bar magnet. This is the south pole. So from north the lines of forces comes out and enter to the south pole. From north they comes out and enter to the south pole like this due to this bar magnet. You can draw also the lines of forces more, but I have drawn only two lines of forces. So at which point? So this bar magnet has this the axial line, this is the equatorial line. Axial and equatorial, you see this is the axial line of the bar magnet and this is the equatorial line of the bar magnet. So at which point, axial line or equatorial line, in which point the magnetic fields of earth magnet and bar magnet, means this black lines of force and this blue lines of force are opposite. Let's see which point opposite. They are going like this, but these are coming in this way, so they are opposite in this side. They are opposite here in this side, they are opposite along equatorial line. But if you see the axial line, lines of forces are going like this, they are entering also the same direction. Here also lines of forces are, you see, lines of forces are coming out. Lines of forces here are also coming out, also in the same direction of this direction, this direction, this direction, this direction, just they are coming out. But here they are opposite. That means when north facing north, the neutral point is at equatorial line. Equatorial line. If you want to find exactly at which point neutral point, exactly at which position neutral point is there, then what you have to do? The horizontal component of Earth's magnetic field is equal to mu naught by 4 pi n by r cube. This is the magnetic field due to bar magnet. This is the magnetic field due to bar magnet at any point on the equatorial line. This is the magnetic field of Earth, horizontal component of Earth. I can write this is the horizontal component of Earth and this is the magnetic field due to bar magnet. Both become, already they are in opposite direction. When the magnitude is equal, then they cancel each other. So neutral point lies at any point on the equatorial line. Now let's come to the second case. When the bit B I am doing here, second case, that is north or south. South facing north. South facing north. North means geographic. South facing north, when it will be written, you will understand it is geographic north. South is facing north. So now I will interchange this magnet's position. So lines of forces also will interchange. Now you see neutral point. The same diagram I am showing to here. This one. I told south pole. This is north pole. South pole is facing to the south facing north. South pole is facing to geographic north. How the lines of forces will be now? You see how will the lines of forces from north, the lines of forces will come out and move like this and will enter to south. One side I am showing it is opposite. Okay. So now you see what happened. So if you see the equatorial line, in this position lines of forces are going like this, also earth lines of forces are going like this, same direction. Check. Is there any chance? Is there any chance of a cancel? No chance of a cancel. But you see this position. In this position lines of forces comes here and here earth lines of forces are going there, but these lines of forces are coming in opposite. So here this is which line? This is the axial line. Neutral point we will find here on the axial line in this situation. When south facing north, neutral point is at axial line. So when the earth magnetic field will be same as bar magnetic field, then neutral point form. So earth horizontal components and bar magnetic field mu naught by 4 pi 2m by r cube. From this you can easily find the distance r from the center of the dipole along the axial line, and you can find the neutral point. Sometimes in exam the numericals come. A bar magnet is placed north facing north, magnetic moment is given, horizontal component of earth is given, find the neutral point. But in this type of condition, neutral point lie on equatorial line. If this type of condition, then if south facing north, the neutral point lie on axial line. It's a very important concept about the neutral point. So now let's come how current carrying solenoid behaves like a bar magnet. Now let's discuss the second thing here. Current carrying solenoid behaves like a bar magnet. Let's draw one solenoid. This is the solenoid. I am drawing the schematic diagram of the solenoid. I want to do the magnetic line supposed to that direction. So here field comes out and here field enter. Comes out means here dot symbol here, and here enter means cross symbol here. Okay, so what happened here? Magnetic lines of forces comes not magnetic lines of forces, I am telling current. Current comes out here and enter in this side. So if current comes out and enter in this side, so here is the magnetic field lines and the magnetic field will be in this direction. This is the axis of the solenoid. Current comes out here and enter here. So this is the axis of the solenoid. We will find the magnetic field at point P, which is at a distance. This is the center of the solenoid. Length you take as L. L is the length of the solenoid, and the radius of the solenoid. We will take the radius of the solenoid. Radius of the solenoid we can take capital R is the radius of the solenoid. Okay, and point P, let's take point P is at a distance of small r. We will find the magnetic field at a distance smaller from the center of the solenoid. Figure now, this figure, everything now you understood. Again I am telling you, I just consider one solenoid where current comes out here and enter through this point. So magnetic fields are in this direction. Magnetic field is in this direction. Okay. So L is the length of the solenoid I choose here. R is the radius of the solenoid. The quantity I took L is the length of solenoid. R is the radius of the solenoid. And P is any point at a distance R, smaller from the center of the solenoid. The question is coming to your mind, why will you find magnetic field at point P? We are going to find magnetic field at point P, but why? We are going to prove that this solenoid behaves like a bar magnet. But what is the purpose of finding magnetic field at point P due to this solenoid? Yes, we will find magnetic field at point P due to this solenoid, and we will compare that magnetic field with the magnetic field of bar magnet along axial line. We will compare that magnetic field with the magnetic field of a bar magnet. If both expressions become similar, then we can say this solenoid behaves like a bar magnet. Can you understand what is the derivation? It will go in which way? We will find magnetic field due to this bar magnet, due to this solenoid. We will find due to this solenoid, and we will compare that expression with the magnetic field due to bar magnet on axial line. If both expressions will be same, then this solenoid behaves like a bar magnet will demand. Okay, so let's find how we will find the magnetic field due to this long solenoid. How we will find that? Okay, that is impossible or possible? Yes, that is possible. How will do? Solenoid consists of many number of circular coils. Solenoid consists of many number of circular coils. Many circular coils are there in the solenoid. Let's choose some circular coil, some bunch of circular coil. Let's choose. Okay. Due to the circular coil, we know the magnetic field at any point on axis. We have done that derivation using Bart-Savart law. Magnetic field at any point on the axis of a current carrying circular coil. Let's choose a small circular coil here. So I choose the circular coil. Suppose at this point, let's choose a small circular coil here. At a distance x from the center. From the center, this is the center here. Okay. From the center, let's choose at a distance x. And width of this circular coil is suppose dx. And within this width, some turns are there. It's not that only I have done only some symbols. Don't think that 1, 2, 3, 4, 5, 6 turns of currents only comes out. No, many number of turns come out. Just I have shown you this pictorial presentation, schematic presentation, only that current comes out. But many turns are there. It's a long solenoid. But I choose a small thickness of a circular coil here. This is small thickness circular coil. How much thickness? Dx thickness. So suppose small n is the number of turns per unit length. If small n is the number of turns per unit length, due to this circular coil now has how many total number of turns? Small n is the number of turns per unit length. It has the width dx. Okay. Then what is the total number of turn? Total turn of circular coil. What I choose? Total turn of circular coil is equal to n dx. Am I right? N is number of turns per unit length. Dx is just the width of it. So number of turns, now total number of turns of circular coil is equal to n dx. We will find magnetic field due to this circular coil at this point. Already we know the expression. You just recall. Circular coil was there, magnetic field at this point. Recall this distance. This is suppose this one radius was r. Okay. Then what is the expression of magnetic field? So mu naught by 4 pi. I think we have taken that as x. Mu naught by 4 pi is 2 nia by r square plus x square 3 by 2 power. This was the expression of magnetic field due to the circular coil at this point. Mu naught by 4 pi 2 nia by r square plus x square power 3 by 2. So we will use this expression for this circular coil what I choose. Then we will do the integration from this to this because we have introduced the variable x. I will do the integration from this end to this end. Okay. Now let's start. Due to circular coil. Due to the coil, what is the magnetic field? I will write the formula dB. I like it dB. So dB is equal to mu naught by 4 pi 2 near number of turns How many turns are there in the circular coil? N dx. Then I is the current passes through it. Okay, we'll choose the I variable here also. Then A is the area of a cross section A, that is pi r square, or you can keep it as A, no problem. That is A divided by r square means radius square. It's right. But what is x? Distance of point P from the circular coil. Here which distance is x? Distance of point P is here. Circular coil is where? Here is the circular coil of center. Circular coil is here. Then what is the distance of circular coil and point P? What is the distance between them? You see, the distance, the whole distance is r from this to this. Then from circular coil, if you see, this x will be subtracted. Here r minus x square. Here x means center to P. We had taken in the Bad-Savart law. But here the distance is the total r minus x. So this is equal to the expression. But the situation is, if the point is far away, because also for bar magnet what formula we had written, that mu naught by 4 pi 2m by r cube. Remember, for bar magnet field formula, mu naught by 4 pi 2m by r cube. There also r is far away. Okay, far away, large distance. If you choose here that this small r is very large, this small r is very large in comparison to capital R, and also very large in comparison to x, then you see dv. We'll neglect all other terms here. Mu naught by 4 pi 2m dx Ia divided by, so these are negligible, this is neglected, then x is also neglected. So what remain here? So this, I think this was r square, r minus x square. Then one power we had left there. The power is 3 by 2. Okay, power we had left there. The power should be also 3 by 2. So now you see, now this expression is similar to this one. So if we neglect this, r square is neglected here. So this x is neglected. What you are getting? R square power 3 by 2. So it's coming r to the power 3. It's coming r to the power 3. This is the magnetic field due to the circular coil, but at a large distance. Okay. So at a large distance you get, but this is only expression due to circular coil. But how will we find this expression for the whole solenoid? To get it for the whole solenoid, we have to do integration. So now we'll integrate it. We have to do integration, integrating both sides. So dv integration, this is mu naught by 4 pi, all the constants take outside, 2n constant, I constant, a constant, this small r is also constant because this is from center to point P. But integration only remain of a dx. This is 0 to b, so answer is coming this side b. But here what limit you will put? From the center we are measuring the distance. This circular coil when you choose at the last, this will be a center total distance L. When you choose at last, this will be plus L by 2. And when you choose to this side, this will be minus L by 2. So value of x will be plus L by 2 this side, minus L by 2 this side. So integration is minus L by 2 to plus L by 2. So this is mu naught by 4 pi 2nia by r cube x. This is minus L by 2 to plus L by 2. Okay. So now next come to the integration is over. So b is equal to mu naught by 4 pi 2nia by r cube. Then this is L by 2 upper limit, then minus, then lower limit. Okay, so it is coming mu naught by 4 pi 2nia by r cube. So L by 2, this will become L. This is now L. So what formula you got here? B expression now, n into L is total number of turns. So mu naught by 4 pi, this is 2, this is n. N small n into L is capital N, Ia divided by r cube. And this one mu naught by 4 pi 2, and this is nothing but m by r cube. So now you see. So this expression is similar to the expression of magnetic field due to bar magnet at any point on the axial line. So current carrying solenoid behaves like a bar magnet. This is the total proof. Sometimes this comes as a 3-mark derivation in exam. So now let's come to the last part of the lecture, that is Gauss law in magnetostatics. You know Gauss law in electrostatics. In electrostatic Gauss law, you know E vector dot ds vector q in by epsilon naught. You know the Gauss law in electrostatics. The flux, electric flux linked with a closed surface is 1 by epsilon naught times charge enclosed by it. The same Gauss also gave another law here, that the magnetic flux linked with a closed surface is equal to 0. Why it is 0? Why it is 0? Now you see how it is 0. Because if at one place north pole is there, lines of forces come out from the north pole. Comes out from the north pole. But at the same place also you will find south pole near it. Same place also you will find south pole, because a monopole doesn't exist. This law proves that monopole doesn't exist. Must be south pole near it, and lines of forces go outside north to south and inside come from south to north. If lines of forces go like this, they will again come. They will go outside the magnet north to south, and inside the magnet from south to north they will come. So when one lines of force is going from north pole, again that lines of force is coming to the north pole to make a closed loop. This is the property of the magnetic lines of force. It always forms closed loop. So when you choose a closed surface, then if one line is going, one line is also coming from the another pole near it. So this indicates monopole doesn't exist. There is no monopole. It cannot exist alone. One pole cannot exist alone. So the Gauss law in magnetostatics says magnetic flux linked with a closed surface is 0, and this proves monopole doesn't exist. Thank you.